Okay, for the lecture material today, what I want to do is not add a whole lot to of material. This is not on the exam, but I do want to get us a little bit down the road and explain to you what enthalpy is. You've seen me talk about enthalpy a couple times this semester, and enthalpy is a definition that we make. So when many times, and so in thermo, we often see the sum of internal energy and the product of pressure. Product of pressure and volume. Okay, so what I'm trying to say is here we have this. We have U plus PV. This shows up a lot. Just this algebraic these ideas show up together like this: U plus PV in many equations. And so these come up a lot, so we just have defined this as H, as enthalpy. Okay, that's what we've done. And so we know that internal energy and pressure and volume, these are all properties. Okay, so what we're going to do is, if we add all these properties together, we're going to call it, this enthalpy is also, so this is a property. It's pretty straightforward there. We're basically trying to just zip all these ideas up and put them in one nice package. So enthalpy is a defined value that will use us, that we will use, that will use us. It really will use us. That we will use to simplify some of our calculations. Okay, that'll become more apparent when we start talking about open systems in chapter 4. Okay, but now we can put this on a unit mass basis, which basically means that we're going to divide by mass, and so we're going to get the specific internal energy plus pressure times the specific volume is equal to the specific enthalpy. Okay, very easy here. Maybe I should make sure that you can see in your notes. This H is enthalpy. Okay, that's what it is. Okay, we can do it on a molar basis. Okay, we could say that U bar plus P times V bar is equal to H bar. That's also working. Remember that bar over the value indicates that it is on a molar basis or per unit mole. Okay, and again, if we have some liquid vapor mixture, if a liquid vapor we can find the enthalpy is equal to the enthalpy of the saturated liquid plus X times Hg minus Hf. Okay, we know that is the case. Now here's one neat thing, and we're going to go to our tables here and figure this out. One neat thing about enthalpy, as we go to our document camera. Oh, we got some kids have messed up. There we go. I'm blaming the children for messing with my camera. We look at our enthalpy tables. Okay, so now what we've basically done today is we've opened up this we've had specific volume is opened up, now internal energy. Now enthalpy is opened up, and notice what they show here. They show saturated liquid, and they show saturated vapor, and then they show something called evaporation enthalpy right between those two. So evaporation is HFG. What that is the enthalpy required to evaporate, to go from a liquid to a vapor. Conversely, we could call this the enthalpy of condensation. It's the enthalpy required to go from a vapor back to a liquid. Either nomenclature works. Okay, what is this number? Look, 2501.4, and this is 0.01. These numbers, this is just this number minus this number. Vapor minus liquid. That's all it is. That's all it is. So it does some math for you to simplify things. So HFG is equal to enthalpy of the saturated vapor minus the enthalpy of the saturated liquid. Okay, so it's Hg minus Hf. So that's kind of interesting. HFG is equal to Hg minus Hf, but that's how we use this. And this is called evaporation enthalpy. It's called enthalpy of vaporization. There's lots of names for it. You can call it the enthalpy of condensation if you go backwards. Okay, all these things give this to you. So what happens is we can rewrite this enthalpy equation as H is equal to Hf plus X times Hfg. Just saves us some time. We don't have to do that subtraction. Maybe that one thing that day that'll just drive you over the freaking edge. You're like, I can't do it anymore. Thermo, I'm not gonna do it. But you say, oh, look, it does HFG. It subtracts it for me. Oh, Thermo, I do love you after all. That's kind of what I'm hoping for. All right, now we're going to use enthalpy significantly in Chapter 4. We talk about open systems, but we can use it now in closed systems, and it is a special case. And I want to alert you once again, it is a special case. So I'm going to say here, this is a special case. It's a special case. And so let me describe this special case to you. Okay, let's look at the first law. The first law says the change in kinetic energy plus the change in potential energy plus the change in internal energy is equal to heat transfer minus the work. Okay, that's what we know. So let's go with our simple situations that we normally deal with, that kinetic energy and potential energy are negligible. That's typically what we have. And so we're left with this equation. The mass times the internal energy at state 2 minus the internal energy at state 1 is equal to Q minus W. Okay? Now, here's where my special case really comes into play here. Let me get back to my color thing. My special case really comes into play. Now we're going to deal with constant pressure work. So constant pressure work. Okay, here's constant pressure work. Well, how do we calculate constant pressure work? Well, work is the integral of PdV. Okay, right? We know that, we've dealt with that many times. Constant pressure work, pressure is going to come out of the integral because it's a constant. We're going to have pressure times V2 minus V1. Okay, we go from 1 to 2. All right. And if we wanted to, we could write this as pressure times mass times specific volume 2 minus specific volume 1. This should be very straightforward, what we've dealt with before in this class. Now, I'm going to take this and I'm going to plug that into here for work, right? For constant pressure work. So this is what my equation is now going to look like. Mass times internal energy 2 minus internal energy 1 is equal to Q minus pressure times mass times specific volume 2 minus specific volume 1. Okay, that's great and all. What happens if we now take this? Now we're going to take this and we're going to move that to the other side of the equation. Well, this is what happens. We get mass can kind of come out of both of these things. And well, let's just write it here first. U2 minus U1 plus pressure times mass times V2 minus V1 is equal to heat transfer. Okay. Now here I see that mass can come out of both these things, so I'm going to have mass times, let's do it this way, U2 plus PV2 minus U1 plus PV1 is equal to heat transfer. And you may be looking at that and say, Dr. Winkle, look at that. U plus PV, that is enthalpy. That is enthalpy right there, and you are correct. Right here, this is enthalpy. This is enthalpy. This is H2, this is H1, and so we can take that and now just write this. Mass times enthalpy 2 minus enthalpy 1 is equal to heat transfer. Okay, so instead of having to look up 4 things, internal energy and specific volume for state 1 and state 2, now we just have to look up 2 things, enthalpy for state 1 and state 2, but only if we have constant pressure work in this specific situation. Okay. Last semester when I brought this up, I gave this equation. Now everybody want to solve every closed system like this. No. Remember up here in my magic equation, this magic rainbow pen, this is a special case. For KE, PE goes to 0 for constant pressure work. Okay, that is important that you understand that. But it can save you lots of time. Now we can really just look up those 2 things and it saves us. And there's some equations that you'll go in, sometimes you'll look at and you can always solve it this way. You can always solve the problem this way or this way. It doesn't really matter. Any way is applicable to solve the problem. It doesn't sound like you say, well, you can only solve it in the way that's in the magic rainbow box. No, you can solve it any way you want to. But there are some times that you're going to be dealing with an equation and you're going to think, I don't have enough information that I can set all these states. I would have to do some sort of iterative process. And let's say, for example, I gave you state 2. You could set state 2, and I gave you the heat transfer, and you need to find state 1. Well, if you look up here and using one of these top equations, you know, this one or this one, there's 2 unknowns, and you'd have to start guessing and testing to figure out how the equation would work. You have to do an iterative process. Whereas if you recognized it and used the rainbow box equation, you could say, oh, I can just solve for H1, and H1 can help me set my state. What I just said to you may not make sense. What I want you to recognize is if you get yourself stuck and you have this, it may be useful to put it into this form, put your solution into this form to help you out of a jam. All right? Again, doesn't matter which way you go about it, they all will give you the same answer. Certain problems are made so that this rainbow box one can really help you. Okay, I think I've repeated myself enough there. I think I've done what I need to do with enthalpy. Again, we're going to talk about it more in chapter 4. Everybody, why don't we say that we just end it here? We'll end it here and go off on, well, there's one more thing I should talk about. I'll use 2 more minutes of time. That's a 15-minute plus a 20-minute. That's pretty good. 45 minutes for today's lecture. Let's talk about enthalpy. We talked about the quality works the same. So quality works the same as it would with enthalpy, internal energy, and specific volume. The X value that you calculate, you don't have to find a new X for internal energy and enthalpy. It's the same X. Okay. You do need to understand that the values of internal energy and enthalpy, they're calculated. They're not experimentally determined. So we can go into that. That's graduate student work we'll be talking about. But for these calculations, you're going to have a reference state with reference values. And so we can see those and we look at our tables. Document camera. Now let's go to R22. That's what I like to show. R22, refrigerant 22. You could see that what we count as our reference value here as 0 is going to be saturated liquid at 40 degrees below 0. Okay, that's what our reference state is. Now we refer to things, our reference state is that enthalpy, that internal energy plus pressure times specific volume. That's what we are using as our reference state. Okay, and internal energy is calculated from that. It may not make sense to you. Why don't we use internal energy as a reference state? Why do we say that? And then because enthalpy is a created value. Well, that's just not the way that this is done. Is you calculate, you take enthalpy minus PV, and you get your internal energy. Okay, so you're going to see these values here. I think we could probably go to R134A. R134A, again, they use negative 40 as their reference value. Let's go see. Let's see if we can press our luck and go to ammonia. Ammonia, it's not on here. That's what I thought. Oh, here it is. Here it is. Here it is. It is also minus 40. Minus 40. So you can see those, and that's how they calculate it. That's I guess those are fun facts to impress your friends. Okay, so that's enthalpy. Gonna close our lecture for today. When we come back on Wednesday, we are going to talk about specific heats. We're going to talk about ways that we can go about solving some problems in a little bit more interesting ways. And then we're going to move on to talking more about some gases. So lots of properties and how we create or how we find properties coming up. If you are having difficulty with these tables, we need to figure it out now, not only for the test but for everything else in this semester. So if you're running into some problems, please get some help so we can work with this. Okay, I'll shut up now and let you get to your weekend, whatever you're doing. Hopefully it's not 11:26 at night and you're watching a thermodynamics lecture lonely. But I guess you do have thermo to keep you company, and what better to keep you company than thermo and your growing and blossoming love for thermo. Maybe you are so in love that you have your appendices and you're sleeping with your appendices, maybe under your pillow, just gently talking to it as you go to sleep. Yeah, I should have shut up a long time ago. Anyway, see you guys later. I'm just realizing that I was calculating 20 minutes plus 15 minutes was 45 minutes. It's actually 35 minutes. Anyway, happy Friday. Happy Friday. See you next week. See you on Monday. Good luck studying for that exam.